Okay, hello everyone. Welcome to week 12 of Intro to Analysis. This week we're going to finish off chapter 6 by talking about uniform continuity. Then we're going to look ahead to chapter 7. We're going to talk about derivatives, differentiability, what it means for a function to be differentiable at a point. And then we're going to prove some results that you have seen or have taught in Calculus 1, like the product rule and things like that. So without further ado, let's go ahead and get started. So the first thing we're going to talk about is the difference between continuity at a point C and uniform continuity. Okay, so recall our definition of continuity at a point C. If we have a function from A to the reals, and it's continuous at a point C in our domain A, if for every epsilon bigger than 0, there is some delta bigger than 0, so that for all x in our domain, whenever x is in the delta neighborhood centered at C, well, that implies that f of x is in the epsilon neighborhood centered at f of C. Okay, so that's what continuity means. And so uniform continuity is a stronger condition than continuity. It's saying that the function is continuous in the same sort of way. And so, what that means is that for every point in your domain, you can use the same delta neighborhood. Whereas with regular continuity, sometimes our delta neighborhood depended on what C we chose, right? We had examples where, like with x squared, we had to pick the minimum of, for our delta value, we had to pick the minimum of 1 and then something else that depended on C. But with uniform continuity, your delta neighborhood can be used everywhere. Like, you don't need different delta neighborhoods in different spots. Okay, so let's examine this definition and compare it to the definition of regular continuity. So it says a function from A to R is uniformly continuous if for all epsilon bigger than 0, there is some delta bigger than 0, such that for all C in A and for all x in A, whenever x is in the delta neighborhood centered at C, this implies that f of x is in the epsilon neighborhood centered at f of C. So the big difference between the definition of normal continuity and uniform continuity is that we have this for all C, okay? So it says some single delta is going to work for every single C, okay? Depending on, what your epsilon choice is. So here's the key difference written out, and I said this aloud, but here it is written down. For regular continuity, delta may depend on your point C. And we saw that with x squared, I think, in the last lecture. We chose delta to be the minimum of 1 and something that depended on C. But for uniform continuity, one delta works for every C in your domain. Okay, so let's look at what this means pictorially. So here I have a picture that illustrates uniform continuity. So notice that I have, I have 4 points, 1, 2, 3, 4. And so these are corresponding to some C values. Maybe this is C1, this is C2, another point in our domain, C3, and C4. Okay, and so uniform continuity says that no matter which epsilon neighborhood I give you, now the epsilon neighborhood is always the same, if you notice around all of these f of ci's. So I give you an epsilon neighborhood and a single delta neighborhood will suffice. A single delta neighborhood will suffice. These delta neighborhoods are the same exact size, right? If you were to project them down here, they're all the same width, okay? And so remember what that uniform continuity definition told us. It says that it says that a single delta neighborhood will suffice, so that whenever you have x that lands in your delta neighborhood, so let me draw that, let me project it down here. So whenever x is in here, then f of x, when I look back up, f of x better be in my epsilon neighborhood. Okay, and so uniform continuity says, hey, the same delta is going to work at every point. So this is an example of a uniformly continuous function. Now over here, this is not uniformly continuous because I give you an epsilon neighborhood. And by the definition of uniform continuity, I should be able to find a single length delta neighborhood that works for everybody, that works for every point, that says, hey, whenever x lives in this neighborhood, so let's project it downwards. So here's my neighborhood here, and I'm going to project downwards here. So whenever x lives in here, so here's all my x's, f of x, when I look back up on my curve, better be in that epsilon neighborhood. And it does work for this one, and it does work for this one as well. But notice that we have a point C3, I'm just calling it C3 over here, some point C, and it doesn't work for this delta neighborhood. Actually, we need a smaller delta neighborhood to make it work. Because if we project downwards this delta neighborhood, so I have this guy and this guy, and uniform continuity, or continuity in general, says, hey, all of these x's, when you look up at their image on the curve, that image better be in that epsilon neighborhood. But check this out. This guy right here and everybody up here does lie in this neighborhood, very close to the endpoints visually, but nevertheless still lies in the neighborhood. But if you look at its image on the curve, it's not inside of that epsilon neighborhood. So this is not uniformly continuous. So let's take a look at an example of a uniformly continuous function. Any linear function is uniformly continuous, and intuitively what you can think about is that there's no great change in steepness along this line's journey, right? It's uniformly continuous. It grows in a uniform sort of way. Now, let's go ahead and prove this. All right, so the proof we want to show for every epsilon bigger than 0, there exists a delta bigger than 0, so that for all, okay, c in the reals, and for all x, whenever x is in this delta neighborhood, this implies that f of x is in this epsilon neighborhood centered at f of c. Okay, and so as usual with these sort of proofs, we can do the scratch work. So we can start with f of x minus f of c less than epsilon. And our f of x is 5x plus 2. So this becomes 5x plus 2. F of c, we just replace c with x. So this is 5c plus 2. Want that less than epsilon. And we simplify. So this is going to give us 5 times x minus c. And then the 2's are going to cancel. Less than epsilon. We can pull the 5 out of there. And we get x minus c is less than epsilon. Isolate the x minus c because that's what's less than delta. And I get x minus c is less than epsilon over 5. Okay, so choose delta. Choose delta equals epsilon over 5. And the result will follow from this. And notice that our delta that we're choosing does not depend on c. Does not depend on where we're at in the domain. It only depends on the epsilon neighborhood that is given to you. So this is uniformly continuous, and you can see it just by noticing that delta does not depend on C. Okay, it doesn't depend on where you're at in the domain. I'm just going to put and the result follows from the scratch work, since we know how to write these proofs formally now. Follows from the scratch work. Okay. Therefore, f of x equals 5x plus 2 is uniformly continuous on R. Okay, so any C will work here. Okay, let's go ahead and look at another example. So I want to give you an example that is continuous on the domain 0 to infinity, but is not uniformly continuous on 0 to infinity. And the classic example that people usually talk about here is f of x equals x squared. Okay, and so let's talk about the intuition of why it's continuous but not uniformly continuous. Well, for continuous, we know what the picture of x squared looks like. It's just a parabola. And so, intuitively, continuity just means I can draw the whole graph without lifting up my pencil. There's no holes or, asymptotes or anything like that. So it is continuous indeed on 0 to infinity, but it's not uniformly continuous. And the reason is because what you can think about is when this parabola grows, like if you think about the rightmost picture of this parabola, it's going to start getting really steep, okay? And that steepness is going to cause us to have to change around our delta neighborhoods. The delta neighborhood that worked here is not going to work here, right? Because if we consider this C1 on the less steep part of the curve, I say, okay, well, this delta neighborhood is going to work because everybody that lies in this neighborhood, when you project up on the curve, actually lies in the prescribed epsilon neighborhood. But that same neighborhood won't work for the other point that I have drawn here. And let me get my picture back. There we go. The other point that I've drawn here is C2. And again, same epsilon neighborhood is prescribed at every point. I know it might not look like the same distance between the purple curves, but imagine that it is, that I can draw nicely. And so what you notice is that this delta 1 is not going to work here, because if we were to make it the same distance, by definition, everybody in this neighborhood, when you project up to the image, should be in that epsilon neighborhood. But look at this guy. It's not. It's not up in here, okay? So we need to compensate for that. We need a smaller delta neighborhood. And you can see pictorially that I've drawn it smaller so that when I project up to the image on to the curve, everybody is going to fall in this this purple neighborhood. Okay, so that's the point here. We need smaller and smaller delta neighborhoods. The steeper your x squared curve gets. And so let's first show. So we claim that f of x equals x squared is continuous on 0 to infinity. Okay, and so, we just do the same kind of scratch work. We want to show that x minus c less than delta is going to imply that f of x minus f of c is going to be less than epsilon. So doing some scratch work here, we have f of x is x squared, f of c is c squared. Want that to be less than epsilon. And then we can use the difference of squares to factor this guy to give me x plus c, absolute value, times x minus c, absolute value. That's less than epsilon. Okay, and so the issue here is something that we've run into before. If we try to isolate the x minus c to get what our delta needs to be, we end up getting something in terms of x, and that is just not going to work because our delta can depend on c with continuity, but it cannot depend on x. Okay, so we have to bound x plus c, absolute value. And the easiest way to do this is to just choose a delta. I usually pick delta equals 1 unless it gives me a problem. So if delta is equal to 1, then what's going to happen? Well, x minus c less than delta is going to imply that x minus c is less than 1. And this is going to imply that x minus c is between 1 and negative 1. And so that implies x is between 1 plus c and c minus 1. Adding c, I get that x plus c is between 2c minus 1 and 2c plus 1. And taking the absolute value, this gives me the result that x plus c, the absolute value of x plus c, must be less than 2c plus 1. Okay? And so this is what I'm going to choose my other delta to be epsilon over 2c plus 1 to ensure that that my delta doesn't depend on x. Okay? So we're going to choose, we're going to let epsilon be bigger than 0 and choose delta is equal to the minimum of 1 and epsilon over 2c plus 1. Okay, and then the result will follow because we have both things are true. We have x minus c less than delta, since delta is the minimum in this set. It means that if we have x minus c less than delta, this is going to imply that x minus c is both less than 1 and x minus c absolute value is less than epsilon over 2c plus 1. All right, so these two things follow from how we chose delta. And now, if we take f of x minus f of c, well, we just get x squared minus c squared, difference of squares. And since this is less than 1, and this is less than epsilon over 2c plus 1, remember that this being less than 1 implied that x plus c was less than 2c plus 1. So putting this and this together in our proof down here, we get that this is less than 2c plus 1 times epsilon over 2c plus 1, and of course this is equal to epsilon. And so f of x equals x squared is indeed continuous on 0 infinity. Okay, and so now I want to claim that it is not continuous on, uniformly continuous on 0 infinity. So how are we going to do that? Let's go ahead and erase some things. So again, we want to show that I'm able to find a c so that so that the same delta neighborhood can't possibly work for this c. Okay, so let me show you what I mean here. Okay. All right. So let's go ahead and scroll back up here. Okay, and so now we want to claim that x squared is not uniformly continuous on 0, infinity. Now it turns out it is uniformly continuous on any bounded interval, but this is an unbounded interval, so it's not going to work here. Okay, so what do we want to show? Okay, we want to show if we negate the definition of uniform continuity, what does that mean? Well, that means that for all delta neighborhoods, there is some epsilon, so that for every c, so for all points in my domain, x minus c less than delta is going to imply that the distance is not less than epsilon, right? Because we're looking at the negation here, but the distance is going to be greater than or equal to epsilon, okay? So we want to figure out what c, so maybe I should write it like this. Let's erase this. Figure out what c is for this statement to hold. Okay, so we want to break the definition of uniform continuity by showing that there is some c for which this holds true. Okay, and so the idea here is, all right, so let's proceed by contradiction. Okay, and so what we're gonna do, well, before we do that, let's go ahead and figure out what our epsilon is gonna be. So remember, for uniform continuity, I should be able to give you an epsilon, and you should be able to give me a single delta, so that whenever x is in that delta neighborhood for all c, for all x, f of x is going to be in that epsilon neighborhood. So let's see how this can fail. So I'm just going to pick a random epsilon. So we're going to choose epsilon equals 1 over 10. And I'm going to do some scratch work to see what c needs to be for this to hold. Because if this holds, then it's not uniformly continuous, right? So let's choose epsilon equals 1 over 10. And let's just do some scratch work. So our scratch work, we're trying to figure out what c needs to be for this to fail. Okay? If there was such a delta, if this thing were uniformly continuous, then this would have to be less than epsilon for every c. Okay? And so for our scratch work, if we look at f of x minus f of c, we have x squared minus c squared greater than or equal to epsilon, which in our case is 1 over 10. And so we can, do the difference of squares thing and say this is x plus c times x minus c greater than or equal to 1 over 10. Okay. And if I isolate my x minus c, because remember I have this up here that x minus c better be in my delta neighborhood for this hypothesis, I get x minus c is bigger than or equal to 1 over 10 times x plus c. Okay. Let's write that a little bit neater. Okay. Okay. And I'm not choosing a delta here. I'm assuming that that delta is given, and I'm going to show by contradiction that this function can't possibly be uniformly continuous on 0 to infinity. Okay, so we have this much, right? This is just our scratch work. We're trying to figure out what C needs to be for this inequality to hold true, and therefore for uniform continuity to fail. So let's go ahead and think about where x plus c is with a prescribed delta. Well, if I have that x minus c is less than delta by absolute value, that says this is between delta and negative delta. And then just adding c, get delta plus c over here, and then c minus delta over there. Okay, and so again, I'm just doing scratch work here to simplify things. So that gives me that absolute value of x plus c is going to be less than delta plus c, right? Okay, delta, oh wait, I'm sorry, I think it should be delta plus 2c. I forgot to add the other c. So absolute value of x plus c is going to be less than delta plus 2c. All right, and so what happens when we take the reciprocal? Well, the sign's going to flip, right? So that's going to tell me that 1 over x plus c is going to be greater than 1 over delta plus 2c. And what's nice about this whole problem is that I don't have to worry about stupid signs flipping on me, right? Because delta is always positive, and c is going to be something in our domain, which is from 0 to infinity, which is also positive. So I don't have to worry about all of that commotion. So I have this guy, and so I'm going to just go ahead and sub it in right here for this absolute x plus c. So this is going to be greater than 1 over 10 times delta plus 2c, okay? Okay, and I want to get rid of the x's somehow, so let's go ahead and define an x in my delta neighborhood centered at c so that I can figure out what c needs to be, right? I don't want to deal with this x variable. I want to eliminate it so that I'm only in terms of deltas and c's. And so let's go ahead and choose an x in this neighborhood. Well, I know that x is between delta plus c and c minus delta. And so certainly if x is here, then x is also, well, let's draw it out actually. So here is the neighborhood centered at c, and here is my c minus delta, and here's my c plus delta. And so if x is in this neighborhood, then it's certainly going to be in this neighborhood. The neighborhood centered at c, or I should actually just draw it in here. So this is the delta over 2 neighborhood. So this is c c plus delta over 2, c minus delta over 2. So I'm just I'm saying, okay, I'm choosing an x that is in this neighborhood, okay? And the neighborhood, I'm gonna choose an x in this smaller neighborhood that is contained in the bigger neighborhood, right? So I'm choosing an x in this neighborhood. I'm gonna say define x to be c plus delta over 2. And I guess it's technically not in this smaller neighborhood, but it's on the edge of it, but it's certainly contained in this delta neighborhood, and that's all we need for our hypothesis. So if I define x to be this, again, the whole point is to get rid of variables so that I can figure out a c that is going to make uniform continuity fail here. So if I define x to be that is certainly contained in this delta neighborhood, right? Certainly contained in it by the picture. And so if I do some replacing here, that gives me that c plus delta over 2 minus c is bigger than 1 over 10 times delta plus 2c. Okay, and now I can simplify things. These c's cancel, and that's awesome. And I get delta over 2. I don't need absolute values because delta is positive, greater than 1 over 10 times delta plus 2c. And my mission here is to figure out what c is. Now, I think I should have put maybe greater than or equal to here, but whatever. Okay, so let's find a c that works here. And so if you do the math, if you do the algebra and isolate c, you get that c is greater than or equal to 1 over 10 delta minus 1 over 2 delta. Okay, and so this, if we take off something positive from this guy, well, it's, that's going to be less than this guy, okay? So for any c, so that this holds, that's going to make this uniform continuity condition fail. I'm going to get absolute f of x minus f of c is bigger than or equal to epsilon. And so I don't have to add this piece on because that's just telling me, okay, take something away from this. So I can simply say if c is larger than 1 over 10 delta, then what happens? Then by our scratch work, if we choose a c that is bigger than 1 over 10 delta, this is going to imply that whenever x is in this delta neighborhood, we have that f of x minus f of c is actually going to be bigger than or equal to the epsilon that we chose, which was 1 over 10. Okay, and so therefore, f of x equals x squared is not uniformly continuous on 0 to infinity. And the way you can think about this intuitively, the way you can think about it is when we had continuity. So let me erase this and write it here. With continuity, we had to choose delta to be the minimum of 1. And what was it? It was 1 over 2c. Yeah, okay. Yeah, epsilon over 2c plus 1. So remember, with continuity, we had to choose delta based on the c. Okay? Which is smaller, 1 or epsilon over 2c plus 1? And so you can think about this. When c gets bigger and bigger and bigger and bigger and bigger, this whole thing is going to shrink smaller and smaller and smaller. And so the further out you go, the further out your c's go, the smaller your delta neighborhood must be. Okay? So that's something that's not uniformly continuous because it depends on where your c value is. So now this is a nice result, okay? And the result, and we're going to prove it in a moment, is that if you have a function that is continuous on a compact set, or in other words, a closed and bounded set, then it's going to be uniformly continuous on that set. And let's see why this is the case. Okay, so we want to show that for all c in our interval that we're given, 1 to 4, and for all epsilon bigger than 0, there's a single delta that depends on epsilon. So there's a single delta such that x minus c less than delta is going to imply that f of x minus f of c is less than epsilon. Okay? And again, we just follow through with our scratch work. Again, we have this difference of squares business, and so we're going to do the same thing that we did before. And this is going to imply that we have x minus c is less than epsilon over x plus c. Now, here's the key observation. X and c are just things in our domain. Our domain is this compact interval from 1 to 4, closed. And so we can bound x plus c based on our interval, whereas before we could not. We had an unbounded interval. So, how can we, what's the bound we can put on this? Well, we say that we have that x plus c is going to be less than or equal to what? What is the maximum that we could have? Well, you could have 4 plus 4, right? That would give us 8, and that's going to be the maximum of x plus c. So we could have two things at the end point here. Right? Because x is less than or equal to 4, and c is less than or equal to 4. And so this is absolute value of 8, which is 8. And so that tells us that x plus c is going to be less than or equal to 8. Okay? Less than or equal to 8. So, now that we have this bound, we can do the computation. Okay? So now we have that. So here's our proof. Let epsilon be given. And we're gonna, let's see, need to show that x minus c less than delta is going to imply that f of x minus f of c is going to be less than epsilon. All right, so f of x minus f of c, we have x squared minus c squared, which factors into x plus c, x minus c. Oh, I forgot my intermediate step. Sorry. We're going to choose delta to be epsilon over 8. Sorry, I forgot to put that right there. Okay. So we have this guy. And so if x minus c is less than epsilon over 8 and x plus c is less than or equal to 8, then combining those things, we get that this is less than epsilon over 8 times 8, which is equal to epsilon. And so it's uniformly continuous. Our delta completely depends on epsilon and not c. And therefore, f of x equals x squared is uniformly continuous on this closed and bounded interval from 1 to 4. So now we have a big result here that says that if we have a function whose domain is a closed and bounded set, okay, compact in the real numbers, to the reals, it's continuous on that compact interval, then f is uniformly continuous on that compact interval. And so we're going to prove it by way of contradiction. And suppose for the sake of contradiction, that f is continuous, but f is not uniformly continuous. That f is continuous on AB. Oops. What happened? Okay, let's see. continuous, let's make sure I'm still recording. Okay, good. On AB, but not uniformly continuous. And so we have to negate what it means to be uniformly continuous. And I'm looking back at the previous segment, and I think I may have said the negation wrong. So this is the correct negation. So how do we say, so uniform continuity says that there exists a delta neighborhood, so that for every C and for every epsilon, that f of x is going to be in the epsilon neighborhood. So we can negate that by saying, then there exists, not for all, but there exists some positive epsilon, so that for any neighborhood that you give me, for all delta neighborhoods, there is a C. Okay, and we found a C in the other one. I think I said in the previous for all C, but no, there exists a C is the negation, such that x minus C less than delta implies that f of x minus f of C is going to be bigger than or equal to epsilon. Okay, so that is our negation of the uniform continuity statement. All right, so we're going to consider the following. We're going to look at some sequences here. Okay, and so we're going to say, okay, well, if this is true right here, then I'm just going to pull this down to sequences, because it says, hey, for any delta bigger than 0. So why not let delta depend on some capital N? So consider x sub capital N minus c sub capital N, where these are just guys in our domain. And this is going to be less than delta, which is going to be 1 over n. Okay, so for all delta, this is true. So certainly delta equals 1, delta equals 1 over 2, delta equals 1 over 3, and so forth. This should be true. Okay, so this should imply that f of x capital N minus f of Cn is going to be bigger than or equal to epsilon. And xn and Cn are living in our compact interval from A to B for each n. Okay, so what does that mean? Well, if these guys are in a compact interval, they're bounded below by A and they're bounded above by B. Okay, so we can say that they are bounded. So these sequences, x sub n and c sub n, are bounded. Okay. All right, so now we're going to bring up a result that we haven't talked about in quite some time, the Bolzano-Weierstrass theorem. Okay, so what does it say? Well, it said that if you had bounded sequences, they had a convergent subsequence. Okay, so by Bolzano-Weierstrass, don't know if I'm spelling that right, and that was page 102 in your text. That means that x sub n has a convergent subsequence. So say the convergent subsequence is x sub nk, and this converges to L. Okay. Now we're going to use another result, which says that compact sets contain all of their limit points, or even more generally, closed sets contain all of their limit points. So we have a limit point L. We have that x sub capital N was in our compact set A to B, and so the subsequence, of course, will be in the compact set if the original sequence is. And that means that that set has to contain all of its limit points since A, B is closed. Okay, so let's write that out. So since A, B is closed, it contains all of its limit points. It contains all of its limit points. That was a tongue twister, unexpected tongue twister. All of its limit points. And that is that's on page 154 in your text. Okay, and so we conclude from this that L, that limit, has to be an A, B. Okay, and so because this subsequence converges to L, we can write this in terms of what does it mean for sequences to converge. Okay, so since the subsequence x sub nk converges to L, there exists a capital K, so that whenever this subsequence is far along enough, so that whenever k bigger than capital K, this is going to imply that this subsequence, the distance between that subsequence and L is going to be less than epsilon over 2. So I'm purposely choosing epsilon over 2 because we're going to do our famous epsilon over 2 trick here. Okay, and so I'm going to label this up here. I shouldn't have labeled this star. I'm going to label this star right here. All right, and so by star, we have A sub nk minus C sub nk is going to be less than 1 over nk. Okay, just looking at what this says right here and subbing in the subsequences. And so let's see. So the idea here is that we're going to choose capital K large enough so that this guy is less than epsilon over 2. Okay, so choose capital K large enough. Okay, so it might even have to be larger than what we said it was here, but make sure that it's large enough so that this is true, but that also 1 over nk is going to be less than epsilon over 2. Okay? And we can do this by the Archimedean principle. No problem. Okay, and here comes the trick. Then k bigger than capital K is going to imply the following. Well, we can rewrite C sub nk minus L in a sneaky way. This is C sub nk minus x sub nk plus x sub nk minus L. And by the triangle inequality, this is less than or equal to absolute C sub nk minus x sub nk plus absolute x sub nk minus L. This is just the triangle inequality. And we already said up here that this guy is less than 1 over nk. We chose k enough. We chose k large enough so that this was less than epsilon over 2. And so this guy is going to be less than epsilon over 2, just keeping in mind that this is the same thing as this by absolute value. Loss by absolute value, period. Yeah, I don't know. So this is going to be less than epsilon over 2 plus, well, we know that x sub n minus k converges to L, and we have up here that our k is large enough so that it satisfies both this and this. We can certainly make k large enough to satisfy both of those two things. So that's less than epsilon over 2, which equals epsilon. And so we have that, by definition, CNK is going to converge to L. Okay, and so here's the kicker. Since XNK converges to L and F is continuous, well, remember, by the sequential criteria for continuity, that's going to imply that Fxnk is going to converge to F of L. And since Cnk converges to L, that means that F of Cnk is also going to converge to F of L. And what can we conclude from there? Well, if both of these guys converge to F of L, let me go ahead and erase some things so I can write more stuff up here. So remember from our above inequality, this was our assumption right here, right? F of x minus f of c bigger than or equal to epsilon. Okay, so if we rewrite this in terms of our sequences that we just found, we have f of x and k minus f of c and k had better be bigger than or equal to epsilon, okay, for each k. Now, if we let k go to infinity, right, we're just looking at convergent sequences here. If we see what it converges to, well, we said this converges to FL, this converges to FL. Well, that implies that this goes to FL minus FL, and that better be bigger than or equal to epsilon by our assumption. But this is going to be 0, okay? And so we have 0 is bigger than or equal to epsilon, which is a contradiction. Epsilon was assumed to be bigger than 0, and therefore, what were we even trying to prove? Therefore, if you have a continuous function on a compact set AB, it will be uniformly continuous on that compact set. Okay, and so the result follows. And I'm not going to write that, but the contradiction tells us that our original assumption that f was not uniformly continuous is wrong. Okay, so it must be uniformly continuous. Okay, well that was fun. We talked about continuity, uniformly continuous, that kind of things. The next thing we're going to talk about are derivatives. So, everybody loves derivatives, right? Because they're super easy to work with. If you've taught Calculus 1 or if you've taken Calculus 1, you know that the most annoying part of Calculus 1 is at the very beginning and at the very end, I think, in my opinion. Because at the very beginning, you're teaching students how to use the limit definition of the derivative. And then when you give them, like, the shortcuts, like the power rule and stuff, they get angry and they're like, why'd you teach me that limit definition? But yeah. And then I guess at the end, maybe what's annoying at the end of Calc 1? Maybe like solids of revolution is kind of hard to learn. I don't know. But anyway, we're going to talk about derivatives and give it a little bit of an analytical twist. So we're going to prove some of these things that we teach our students in Calc 1. Okay, so let's go back with some definitions. Definition 7.1. So you have an interval, I. When I say interval, I mean something like AB, or maybe negative infinity to A, or AB, something like that, etc., etc. Anything that looks like that, or it could be open AB. And you have a function from that interval to the real numbers, with c being in that interval. We say that if f is differentiable at c, if the limit as x goes to c of f of x minus f of c over x minus c exists. Okay, so remember with these derivatives, we're just looking at slope, really. We're trying to compute the slope of this tangent line to a point, and the idea is to let the distance between x and c get smaller and smaller so that the distance between f of x and f of c gets smaller and smaller so that your slopes of your secant lines approach the slopes of your tangent lines. That's the idea here. And so we say if c is the collection of points at which f is differentiable, then the derivative of f is the function f prime going from the set c, where c is the points that are differentiable, to the real numbers, where f prime of c is going to be this limit. Okay, so that is the definition that you give your students, and they hate you for it, but let's see how we can use this to prove some results. Okay, so let's go ahead and prove the power rule that we teach our Calc 1 students. So if you're taking the derivative of x to some power, you just move the power to the front and subtract 1, and that's the power rule. So let's go ahead and prove it. So we want to show the following. We want to show that f prime of c is equal to this guy. So if we just use the definition of what it means to have the derivative of f evaluated at c, that's just going to be the limit as x goes to c of f of x minus f of c over x minus c. And so we can replace the top with x to the n minus c to the n. So this is the limit as x goes to c of x to the n minus c to the n over x minus c. And so if we look at the top and we just do some scratch work off to the side, we'll notice a pattern here. When n is 1, we get x minus c. When n is 2, we get x squared minus c squared. And so forth and so forth. When n is 3, we get x cubed minus c cubed. And so this is going to equal x minus c plus times x plus c. This guy is going to equal x minus c times, maybe I should put it down here. Let's see. Let me give myself some more room. So x cubed minus c cubed. If you carry out the division here, you get x minus c times x squared plus cx plus c squared, and so forth. X to the fourth minus c to the fourth, let's just do one more, is x minus c times x cubed plus cx squared plus c squared x plus c cubed. So in general, we can say that x to the n minus c to the n is equal to x minus c times x to the n minus 1 plus x to the n minus 2c plus dot 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 plus x to the cn minus 2 plus c to the n minus 1. Okay? So if we go ahead and replace the numerator with this expression, and again, I'm just looking at the division by x minus c. And anyway, I can replace the numerator with that guy, and so some things are going to cancel here. So I have x minus c times x to the n minus 1 plus x to the n minus 2 times c plus dot 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 plus c x to the c to the n minus 2 plus c to the n minus 1. Okay, and so that's the top. On the bottom, I have x minus c, so those guys can cancel. And now I'm just left with a continuous function. Remember, we proved that all polynomials are continuous functions. And with continuous functions, we can just plug in what the what x is approaching to get the limit of that function. All right, so let's go ahead and do that. So we have a function of x, and we're going to plug in c anywhere we see an x. So that's going to give us c to the n minus 1 plus, if I plug in c here, c to the n minus 1 times c is just c to the n minus 1. Or I said c to the, I meant to say c to the n minus 2 times c is c to the n minus 1. Okay, and we're going to have c to the n minus 2 times x, which is c, and so that's going to give us c to the n minus 1. And what you should notice here is that we are going to have n c to the n minus 1s. This is n c to the n minus 1s, right? Because here's a c to the n minus 1 to start out with, and each of these terms are going to collapse to c to the n minus 1. And there's n minus 1 of those there. So in total, there are n minus 1 c to the n minus 1s plus this guy, so that's n c to the n minus 1s. Okay, and we're done. So we found that f prime of c was indeed equal to n times c to the n minus 1, and so we've shown the power rule. Okay, let's look at a theorem here. Suppose that I is an interval and we have a function from I to r. It's differentiable at c in the interval I, and we claim that this implies that f is continuous. Now the other way doesn't hold true. If a function is continuous, it is not necessarily differentiable, as we know from our absolute value function. If we have a cusp anywhere, it is not differentiable at that point, but the absolute value function is continuous. So the converse does not hold in general. So let's go ahead and prove this. And so what are we going to do? We're going to suppose that f is differentiable at c. Okay, well, if it's differentiable, we can look at the derivative function and evaluate it at c. So then f prime of c is going to equal the limit as x goes to c of f of x minus f of c all over x minus c. Okay, and we know that since it's differentiable, this limit at c, this limit exists. Let's call it L. Okay, so what are we trying to show? We're trying to show that f is continuous at c, and so remember those criteria for continuity that we looked at a few lectures ago. There were 5 of them, and the very last one said that we need, if we want to show that f is continuous at c, we need to show that the limit as x approaches f of x is equal to f of c. The limit as x approaches c of f of x equals f of c. I meant to say. I'm saying dumb things today. So this was on page 187. It was the last criteria for being continuous. Okay, so we want to show this. And the reason we're going this way is because this kind of looks like this, something that we have. All right, so from our given assumption, we have that the limit as x goes to c of f of x minus f of c, well, because f of c doesn't depend on x, this is going to equal the limit as x goes to c of f of x minus f of c. You see what I mean? Like when you're taking the limit of f of c, we don't have an x involved, so it's simply going to be f of c. All right, and then we do some trickery, right? This is the same thing as the limit as x goes to c of f of x minus f of c over x minus c times x minus c, right? Just writing f of x minus f of c in a sneaky kind of way here. And we can use the product limit laws to separate this stuff out into a product. So this is equal to the limit as x of c, right? The limit of the products is equal to the product of the limits, is what that limit law said. This is the product limit law. I think the book says funky limit laws. I think that's one of them. Okay, so this is equal to limit, and then we have this guy over x minus c times the limit x goes to c x minus c. Okay, and what did we say here? We said here that we know that this limit right here is equal to L by our assumption. So this is equal to L times, well, x minus c is certainly continuous everywhere. So we can plug in, we're allowed to plug in c for x to evaluate this. So this is just c minus c, which is 0. So this equals 0. And we have shown our claim, right? Because we were trying to show this, but this is if and only if. If I subtract f of c, I get limit f of x minus f of c equals 0. And this is as x goes to c, which we said was equal to this, which we said was equal to this. So we indeed get 0 here, and so f is continuous at c if it is differentiable. Okay, and so as I mentioned, the converse doesn't hold. So being differentiable doesn't, being continuous doesn't imply differentiability. And we can see this with the absolute value function. As I said, this guy just has this sharp corner here. And so the idea is like the slope here is not well defined, right? What is the slope of the tangent line to this point? You can't really say because you can draw infinitely many tangent lines to that little corner. So the idea here is there's a cusp. Oh, not differentiable. That's the geometry. So let's show this algebraically. It's not hard to show that this guy is continuous at x equals 0. If we look at the limit as x goes to 0 of f of x, well, we can just see from the picture that this is 0, right? So this is equal to f of 0, which is 0. Not too hard to see that is true. So let's show that it's not differentiable at 0. All right, so taking the derivative. So if it were differentiable, the derivative would exist. So if we take the derivative and plug in 0, that limit should exist. And so this is the limit as x goes to 0 of f of x minus f of 0 over x minus 0. So just plugging in what we know. This is limit as x goes to 0 of absolute x minus absolute 0, which is 0 over x. And we know that this limit doesn't exist. I think you guys looked at something pretty similar for a homework problem. And the idea is that we can think of two sequences which converge to 0, but when you take f of those sequences, they converge to different limits. So consider a sub n equals 1 over n. This certainly converges to 0 from lots of problems that we've done with this. But also, b sub n equals negative 1 over n converges to 0 by making this denominator very big. So those converge to 0, but if we look at f of a sub n, this is f of 1 over n, which is just absolute value. So we're looking at this thing, right? So this is going to be, maybe I should have called this a different function. Maybe I should have called it g, because I think we already called, yeah, I should have just called it g. Let's just call it g. Absolute x over x. So g of a sub n is going to be g of 1 over n. This is g. So this is absolute 1 over n over 1 over n, which is, of course, 1. So this sequence, g of a sub n goes to 1. But on the other hand, g of b sub n is equal to absolute negative 1 over n over negative 1 over n. And this guy on top is positive, this guy on bottom is negative, and so this goes to negative 1. Okay, and so by the sequential criteria for limits, the limit doesn't exist. Therefore, f prime of c does not exist. Right? F prime of 0 was just this guy, and this guy does not exist, so f prime of 0 does not exist either. Okay, so it's not differentiable at 0. Okay, so here are some rules that we all know and love, and I'm not going to prove them, but it's pretty straightforward to just use the definitions to prove these. And so the point here is that the derivative function is linear. So if you have the sum and you're taking the derivative, that breaks up into the sum of the derivatives. Okay, so that's here. Same thing with the difference. If you're taking the difference of derivatives, that breaks up into the, or if you're taking the derivative of a difference of functions, that's the difference of derivatives. Okay. If you have k is a scalar, so k is a real number, multiplying it by f and then take the derivative, that's the same thing as multiplying your scalar k by the derivative. Okay, so this is something that I think we all know and we use when we're teaching calculus. But yeah, so linearity. Okay, the next really nice thing is product rule. I had a teacher in high school. Her name is Miss Baird. I don't know if she's ever gonna watch this, but she used to like say this, like, you know, I don't know what they're called off the top of my head now, but they're like sayings to help you remember things. So she would say for the product rule, she'd say, keep the first times the derivative of the second plus keep the second times the derivative of the first. And I swear, that is always on my head. But of course, multiplication commutes, and so does addition. So, you know, keep the first, well, that's over here, times the derivative of the second, that's over here, plus now you keep the second times the derivative of the first, that's over here. Anyway, yeah, Miss Baird was cool. She was a great math teacher. So, that's the product rule. Let's go ahead and prove it, all right? So we can prove it just from using our definition of derivatives and our functional limit laws. So we have the following. We have fg prime of c, just by definition of the derivative, is going to be the limit as x goes to c of fg of x minus fg of c, okay, all over x minus c. Okay, so what does this mean if I have the product of two functions and I'm evaluating at x? Well, that's the same thing as just taking f of x times g of x. So this is f of x times g of x minus f of c times g of c over x minus c. Okay, and then we're going to do a stupid trick, because that's what we do in analysis. We do stupid tricks to make our lives a little bit easier. And the stupid trick I'm going to employ here is I want to somehow, like, if I look at my formula and I'm trying to figure out how to prove this, I'm trying to somehow end up with an f prime of c, which we know is f minus fc over x minus c, and I'm trying to end up with a g prime of c as well. So somehow I want to incorporate an f minus f of c and a g minus g of c in here. But to do that, I have to simplify by complicating. So I'm going to replace the numerator with something a bit longer so that I can factor out and get what I need ultimately. So what I'm going to do instead is I'm going to write this as f of x g of x minus f of c g of x plus f of c g of x minus f of c g of c. So this is the one little trick that is just, it's worth so much. Subtract and add and get 0 to factor out things and make things look how you want them to. Okay, and this is over x minus c. All right, so the point of subtracting and adding this thing is that what I can do next is I can factor out a g of x over here, and so I'm getting close to my f derivative, right? So this is going to be the limit as x goes to c. Factor out the g of x, and I get f of x minus f of c over x minus c. Okay, and then over here, what I can do is I can factor out an f of c. Okay, if I factor out an f of c, I get that this is g of x minus g of c. Okay, so now I'm good, because this guy, what is this? This is f prime of c. This guy is g prime of c. So this equals, I mean, distributing the limit, of course. Maybe I shouldn't have been as sloppy, but this is all in its own parentheses, and the limit laws say that the limit splits among addition. Okay, so this is equal to the limit as x goes to c of g of x f of x minus f of c, okay, for x minus c, plus the limit as x goes to c of f of c times g of x minus g of c all over x minus c. All right, and so this guy is, we assumed, what was our assumption? We assumed that we assumed that g is differentiable. Now, g being differentiable means that g is continuous, and we can just plug in the c, right? So if we just plug in the c for g of x, that's going to give me g of c, taking the limit there. Because g is continuous, we know g is continuous because of the assumption that g was differentiable. Now, that's g of c. Now, when I take the limit of this guy, that's f prime of c. Okay. Now, working over here, well, f of c doesn't depend on x. It's just a constant. So taking the limit as x goes to c does nothing to it. So that's just f of c. And taking the limit as x goes to c of this thing is just by definition g prime of c. And there we have it, folks. Keep the first times the derivative of the second, plus now you keep the second times the derivative of the first. Shout out to Miss Baird. Okay, so there's our product rule. Okay, the quotient rule, I'm going to have you poor unfortunate souls that are in my class prove this for homework. For those of you that are just watching for fun, because, I don't know, maybe you're a little bit sick, this is the quotient rule, and those of you that don't have to do this for homework, it might be a good idea to prove this as an exercise, and as a hint, it's very similar to the proof of the product rule. You're going to do some stupid tricks like this in the quotient rule proof. Okay, so let's go ahead and do some examples where we investigate the continuity and differentiability of some strange functions. Okay, and so this family of functions is called the topologous sine curve. Okay, so it kind of looks like a sine curve, right? But there's some weird behavior that's happening at the origin. So here's our first function that we're going to look at. G naught of x is equal to sine of 1 over x if x is non-zero, and it equals 0 if x is equal to 0. Now, if you're just looking at this thing on Desmos, just plotting it in Desmos, it does sort of look continuous at 0. I mean, there's a lot of blue lines, and so you might think, okay, well, it goes up and down and up and down and up and down. But the weird thing about it is that this thing isn't even continuous at 0. And the reason geometrically or topologically is because it oscillates so much around 0, it can't be continuous. Okay, the neighborhood condition is going to fail quick with this kind of oscillation around the origin. So let's prove that this is not continuous, and then we know that if it's not continuous, it's certainly not differentiable at 0. Okay, but not the other way around, right? So let's check continuity. And you always want to check continuity first, because if it's not continuous, it's certainly not differentiable. Okay, so we're going to check continuity, and we want to see, is it continuous at 0? So we want to show that the limit as x goes to 0 of f of x is equal to f of 0. Right? That's what we want to show. And what is, well, I should have actually not put f here. Let's put g naught. G naught of x is equal to g naught of 0. Now, g naught of 0 occurs when x is 0, so it's 0. So we want to show that this limit right here is 0, okay, to prove that it's continuous. But it's not continuous, as I mentioned. And so let's show that, this limit doesn't exist. Okay. So the limit as x goes to 0 of g naught of x. Well, which piece am I going to use? I'm not going to use the piece at x equals 0, because remember, with limits, I don't care what happens at x equals 0. I care what happens around x equals 0. So I'm going to use this piece here. So I'm trying to find the limit as x goes to 0 of sine of 1 over x. And I think we've done this before, or some sort of variant here where we show that this doesn't exist because of two different sequences converging to 0, but when you apply f to those sequences, they converge to different things. So consider the sequence a sub n is equal to even multiples of pi, or I should say even rotations or maybe we'll just say it like this. Anything that's coterminal to pi over 2 is going to be pi over 2 plus 2 pi n, right? You're only going in full circles, no matter what n is. You're not ending anywhere but at the pi over 2 spot. And also consider this sequence, b sub n equals 1 over 3 pi over 2 plus 2 pi n. So again, here we're at 3 pi over 2, and we look at anything coterminal to it. So if I just draw a little picture here, here's 3 pi over 2. Any multiple of 2 pi is going to end up back at 3 pi over 2. So we know that those guys, the sign value here is -1, and the sign value here is 1, and so that's going to cause some problems for us. Notice that a sub n converges to 0, right? As n gets really, really large, this denominator is getting very small, and hence the whole thing is going to 0. And likewise for b sub n. But if we look at g0 of a sub n, if I just plug in a sub n into my function, I get sine of 1 over a sub n, and 1 over this is simply pi over 2 plus 2 pi n. And we know that the sign of anything coterminal to pi over 2 is going to be 1. While on the other hand, g naught of bn is going to equal sine of 1 over bn, and that's just going to be 3 pi over 2 plus 2 pi n, and we know that this is any angle that's coterminal to 3 pi over 2 will have a sign of -1. Okay, and therefore by the sequential criteria for limits, so we have these two things going to the same thing, but g of the first thing goes to 1, and g of the second thing goes to the -1. So by the sequential criteria for limits, the limit does not exist. And hence, g naught of x is not continuous at x equals 0. Okay, so that's the idea there. It is not continuous, and therefore, let's see what the name of the theorem was. It was theorem 7.1. Okay, so then by theorem 7.1, it's not differentiable either at 0. Okay, so that was that one. Now let's look at another cool example. Okay, now we want to investigate the whether or not this function is differentiable and continuous again at x equals 0. And this time, it's a little bit different because we have a factor of x in the front. And it turns out that that factor of x is actually going to make this thing continuous at x equals 0. So that's kind of interesting. So I'm claiming that this guy is continuous at x equals 0. Notice that we're still oscillating like crazy around x equals 0, but the oscillations are getting smaller and smaller and smaller. And so this is going to allow us to achieve continuity at 0. But I'm going to claim that even though this thing is continuous at x equals 0, it isn't differentiable at x equals 0. So let's go ahead and prove this. So we're going to claim that, and this time it's g1 of x is continuous at x equals 0. So let's show this. And so what are we trying to show for continuity? That fifth limit condition in our list of things that make functions continuous. We have the limit as x goes to 0 of g1 of x should equal the limit, not the limit, sorry, equal g1 of 0, right? That's what it should be. Now, if I'm taking the limit, I'm using this top piece because we don't care what happens at the value that x is approaching. So this is going to become the limit as x goes to 0 of x sine of 1 over x. Yeah, I think we have done this problem before, but I don't know. Maybe you guys maybe you guys don't remember. I don't know. Okay, so we're trying to show it's continuous, so we want to show this limit does exist, and indeed it equals g1 of 0, which happens to be 0. Okay, so we claim this is 0. So our old friend, squeeze theorem says, well, it says, okay, I know that sine of any angle is going to lie between -1 and 1, right? And so if I multiply that middle guy by x, that tells me that x sine of 1 over x is going to be between x and -x. And we know as x goes to 0, this thing goes to 0. As x goes to 0, this thing goes to 0. So by the squeeze theorem, the thing in the middle better go to 0. Okay, and so this thing is continuous at 0 because this limit was 0, and that is exactly what we were looking for. Okay, but I claim that it's not differentiable. So remember, if it's not differentiable, then g1 prime of 0 shouldn't exist. Okay? Not differentiable. So let's go ahead and compute this derivative, or try to compute it at least, and show that this does not exist. So we're going to take the limit as x goes to 0 of g1 of x minus g1 of 0 over x minus 0. And so this is going to become the limit as x goes to 0. g1 of x, okay, well, x is approaching 0. It's not at 0. So g1 of x is going to be the top portion of the piecewise function, and g1 of 0 is 0. So this is x sine of 1 over x minus 0 is 0 over x. Now these x's cancel out, and we're left with the limit as x goes to 0 of sine over 1 over x, which by a previous problem does not exist. Does not exist. Therefore, g1 is not differentiable at 0. Okay, well, thanks for watching, guys. Next time we'll talk more about derivatives and mean value theorem in particular. So see you guys next time.